Today's talk is going to be on higher order adaptive methods for computing exit times of Ito diffusions. And this is a joint work with my supervisor, Hakan Hoel, who's from the University of Oslo, who's working in the Department of. So to get into it, so we first consider a d-dimensional autonomous stochastic differential equation given by the equation here. And we consider that it starts at some position x naught, which we consider to be deterministic for our cases for the purposes of just exemplifying what is to be shown in the numerical results. But I believe we can also consider cases where x naught is sampled from a random distribution. And we consider that this process starts inside a bounded domain, which is in our d-dimensional space. So what is our objective? Our objective is to basically construct an algorithm to efficiently compute the strong approximation of exit times. So the exit time is defined as the time that the process takes in order to exit a domain, a bounded domain. And we consider the exit time definition to be given as such, shown here. So the basic idea behind the algorithm is to use finite time step sizes as the process gets closer and closer to the boundary, depending on the order of the scheme that is employed. And that's where the higher order Ito-Taylor schemes actually come into picture. So what are the applications of exit times? So the very first application comes from physics, which is related to Langevin dynamics, where we are interested in computing the average time that a particle which is in state x1 takes to traverse to state 2, shown here, and back and forth, basically. So we are interested in computing the mean passage time for a particle between the pseudo-stable states. And second application would be related to pricing of barrier options. So what barrier options basically means is you execute the option, or you basically sell or buy an option when the process actually crosses a certain threshold or a boundary. So that's of interest to a lot of people who are working in finance. And the third application would be related to pricing of American options, where we consider a more complex payoff function given by PT. And we are interested in calculating the value of the option related to it. So these are some of the applications that one might be interested in when in relation to computing the exit times of a process. So what are the possible methodologies that one can employ in order to compute the mean exit time of a process? So the first method is to solve the Feynman-Katz PDE, which is pretty simple. You just need to use like finite element methods or any popular method of your choice in order to compute the solution to the exit time problem. But the major issue comes from the fact that as the dimensionality of the problem increases, the cost involved in solving the Feynman-Katz PDE also increases, which is not a good thing. So most people rely on Monte Carlo methods. So that is what we'll be focusing on as well, because they scale well with the dimensionality of the problem at hand. So now that we established what our focus is going to be on, we are interested in computing the exit time of the actual process, which is given by the terminology tau here, using a numerical scheme, specifically a strong Ito-Taylor scheme of a certain order gamma. And we consider that the numerical process is piecewise constant in between times. So that is an approximation that we make. And it has been shown in literature that when using piecewise constant Euler-Maruyama scheme, peak order of the exit time is of order h to the 1/2, basically, where h is the time step parameter. So if you were to use uniform time step sizes, you would get a weak order of order h to the 1/2 and a strong order of h to the 1/2 as well. So there is no improvement. And this can also be seen when using higher order schemes for computing the exit times. So this is not just restricted to Euler-Maruyama scheme. This also like follows along with using higher order schemes. And we'll look at as to why that's the case. Because usually when you use higher order schemes, you should see an improvement in the strong order as well, depending on the type of payoff that you are computing. For our case, for the exit time case, it's not pretty clear as to why using higher order schemes don't yield a good convergence rate. So Giles and Bernal also showed a new method which was relating to conditional multi-level Monte Carlo method in order to compute the exit times of processes. And what they basically do is they spawn more paths just before the process actually exits the domain and compute the conditional expectation based on that. So which basically improves the variance, and you see that you compute the mean exit time using multi-level Monte Carlo method for a lower computational cost as shown here. So these are some of the existing methods related to computing the exit time of a process. So the major source of error is what I wanted to get into. So the major source of error is the numerical process missing an exit when the true process has already exited. So if you can see from the image here, so the true process has already exited at this point of time here, whereas the numerical process exits only here. So there is a discrepancy in the time between when the true process actually exits and the numerical process exits. And if you were to use a larger time step size close to the boundary, you would actually see that you overshoot by a larger time step size, right? So you make a larger error when you're computing the mean exit time, which is something which you don't want. So our idea is to basically use smaller time step sizes as the process gets closer and closer to the boundary. Another smart method in order to improve the weak rate of the mean exit time computation is to shrink the domain by a factor h to the 1/2, some constant times h to the 1/2 basically, in order to improve the weak rate. And this can be coupled with the multi-level Monte Carlo to like improve the performance as well. So getting back to the main idea behind the topic today, our idea is to improve the strong rate for computing the exit times of processes. So we use strong Ito-Taylor schemes of order gamma in order to simulate the stochastic process. So which we represent here by using psi of gamma here, where gamma basically represents the order of the scheme. So for gamma 1, we end up with the Milstein scheme shown here. And for gamma 1.5, we end up with the order 1.5 strong Ito-Taylor scheme. So the time step size that we choose in order to compute the exit time of the process is adapted as the process gets closer and closer to the boundary. So how do we basically adapt this time step size? Is based on the current state of the process. So if the process is closer to the boundary, we use a smaller time step size. And if the process is further away from the boundary, we use a larger time step size. So that's the basic idea behind it. And this time step size is chosen adaptively based on the current state of the process. So here we make an assumption and throughout basically that the diffusion coefficient B has a diagonal structure. So this is basically to help with sampling the higher order noise terms, let's say, given by this term delta Zn here, so that you don't have this Levy area terms that you have to like compute in order to simulate the process. So that's an assumption that we make, that the diffusion coefficient has a diagonal structure. And the numerical scheme is given by equation 2 here, basically. And the red part basically denotes just the Milstein scheme, and the red part along with the blue part basically denotes the order 1.5 scheme. And another assumption we make is related to the cost involved in sampling the random variables delta W and delta Z, which you assume to be of order 1. And delta C is basically given by this terminology here, which is just the iterated eta integral. If you want more details regarding how to sample these random variables, you can have a look at Cloden and Platin, and more details will be provided in that. So this is where we get into this adaptive time stepping idea. So if you look at the image here, like I said, you start at the position x0 and you jump in time using time step sizes h in all these regions. And the moment the process enters the critical region, which is shaded by orange lines here, you start using time step sizes which are smaller. Let's say h square in this case, right? If you just have one critical region, you just end up using h square time step size inside the critical region. And this way, you basically don't overstep by a larger time step size here. So you end up making lower error when you're computing the mean exit time. So the time step size parameter is chosen as h, which is greater than 0, obviously. And we consider two cases, where the first case being we use the Milstein scheme with the critical region parameter delta of h. And the second being the order 1.5 scheme, where we use delta 1 and delta 2. So we basically consider two critical regions which are nested within each other in order to improve the strong rate. So for the Milstein scheme, this is how we basically determine the time step size adaptively. So if you are outside the critical region, we use the time step size h. And if you are inside the critical region here, we use the time step size h square. Similarly, for the order 1.5 scheme, like I said, you consider two critical regions which are nested. And based on which critical region it's inside, you use finer and finer time step sizes. So that's basically the idea. Like I said in the previous slide, we use like smaller time step sizes in order to reduce the overshoot, which occurs as the process exits the boundary. This basically improves the strong rate, as we'll show in the upcoming slides. So we cannot choose this parameter delta, which was shown here, and delta 1 and delta 2 shown here for the order 1.5 scheme haphazardly. We have to be very careful with how we choose delta, because if we were to choose a very large delta, we end up with using finer time step sizes from the very beginning of the evolution of the process. So we end up computing the mean exit time with a high accuracy, but for a high cost as well, which is something which we want to avoid at all costs, because it's not easy to simulate the process using finer and finer time step sizes without significantly getting hit in the computational cost. So we basically want to choose delta and the tuple delta 1, delta 2 in an optimal way, let's say, so as to keep the cost in control and at the same time also improve the error rate. So that can be done by considering that the probability be controlled in such a form. So the probability that the adaptive time step size is not the smallest time step size that we use is of certain order, which is given by the order of the scheme that we employ. So that's the basic idea behind it. And now we get into the nitty-gritty details of actually proving the rates and the computational cost involved with the algorithm. First, we assume that the domain D is bounded and that the boundary of the domain is at least C4 continuous. This is needed in order to ensure that the solution to the Feynman-Katz PD is unique and it does exist. The second assumption that we make relates to the coefficients as such, that the drift coefficient and the diffusion coefficient are at least C3 continuous. And we also assume that the diffusion coefficient is uniformly elliptic and is bounded. So this is a condition that we need in order to basically compute the critical region parameters, which was shown in the previous slide. So this basically helps us bound the probability. So that's something which we need. And it is important to note that for the exit time to be well defined, it is sufficient that the coefficients be just uniformly Lipschitz continuous, but we impose these conditions here because this is needed for the numerical scheme as such in order to implement the 1.5 order scheme. So lemma 1 basically states that for the critical region parameters chosen as such for both the order 1.5 scheme and the order 1 scheme, you can basically show that the probability of using the finest time step sizes of order 1 minus order h to the power gamma. So this is the lemma that is there. And using this, we prove that the theorem that the strong error in the actual exit time is of order h to the power gamma minus some epsilon for some epsilon greater than 0. So this is the theorem that we would like to prove. Now, in order to prove that, we make use of the Feynman-Katz PDE, basically. So recall that this is the exit time of the actual process itself, the process leaving the domain D. And in order to extend this, we introduce this new notation of exit time of a process starting at some time t and position x to the definition shown here. So if you were to start at the final time t, you basically end up with the exit time being 0. And if you start at any position which is on the boundary, you also end up with the exit time being 0. And it is important to note that we are actually interested in looking at this quantity here, basically, where the initial time is 0, and we start at the position which is x0, which is the initial position. So the mean exit time is then given by the function here, which is just the expected value of this stopping time. So that's the PDE which we use in order to compute the strong error rate. So this basically relates to the exit time PDE. So for a given coefficient, drift coefficient A, and for a given diffusion coefficient B, you can basically solve this Feynman-Katz PDE in order to compute the mean exit time of the process. And like I said, the challenge lies in computing this using numerical methods, because as the dimensionality of the problem increases, it's more difficult to compute this. So we make the assumption that the mean exit time is Lipschitz continuous in space, basically. And this is a key assumption that we'll be using in order to generate the bound. So what's the idea behind the proof for the strong convergence rate? First, we are interested in computing the strong error rate given by this term here. So we split it into two components, one relating to the numerical process exiting before the actual process, and the second term relating to the numerical process exiting after the actual process. So for term one, it is important to note that as the numerical process exits before the true process, then you can consider that at the time of exit, the numerical process is outside the domain, which is given by this D complement, and the actual process is still inside the domain. And it is important to note that the difference between the exit time of the actual process and the exit time of the numerical process times the indicator function of the numerical exit time being less than the actual exit time can be written as such. So what does this basically mean? I'll show it in an upcoming image. So if you look at this image here, you see that the red part basically represents the numerical process, and the numerical process has exited at this time here, whereas the exact process is still inside the domain. So in this case, what happens is you can consider that x of nu, which is still inside the domain, and then it evolves from time nu all the way up to time tau until that process also exits. So this orange shaded region basically represents the evolution of the process between times nu and tau. And this is also the reason why we can write tau minus nu to be this terminology here, which is what was stated in the previous slide as well. Now we consider a point y on the boundary of the domain such that the absolute magnitude can be bounded in such a form between the numerical process and the actual process itself. So I'm not going to get into a lot on the proof side of things, but we can show that the term 1 using the Lipschitz continuity property of the mean exit time and doing this change basically which was shown in the previous slide. Using this property here, we can show that the first term is of order h to the power gamma, where gamma is the order of the strong Ito-Taylor scheme that we employ. And it is a key point to note that the exit time of the numerical process is something which is contained inside the set of points generated by the adaptive time stepping algorithm. The term 2 is more difficult to control. So we basically further split it into two other terms. One that has to do with using a time step size which is larger than the smallest time step size possible based on the number of critical regions that you have. And the other term is related to using the smallest time step possible, which relates to the order of the scheme that is employed. So one relates to large overshoot and other one relates to a small overshoot. So as you can see, if you use a larger time step in order to exit, you basically exit using a larger time step size, which means you also commit a huge crime when it comes to the error. So in order to control that, it's pretty easy to control it because the first term can be bounded as such. And this relates to the order h to the power gamma. Term 2 relates to using the smallest time step size, and that would be h to the power 2 gamma. So if you were to use a 1.5 order scheme, you would use the smallest time step size of h cubed. So that would lead to a smaller overshoot. So that's why we label the term 2 as a small overshoot term. And using the smallest time step size, you can show that the second term is bounded as such. So combining all the terms together, we can basically show that the strong error is of this order. Now, it's good that we have a very good order of convergence in terms of strong order when it comes to using adaptive time stepping. But like I said before, the scheme is only as good as the computational cost involved with it. So we would like to minimize the cost that is involved in order to use the adaptive time stepping algorithm. So now we get into looking at the actual cost that is associated to implementing this. In order to do that, we first define the cost of one numerical realization. So if we consider a path which starts at position x naught until it exits the domain, that would be just one trajectory, and we consider the cost associated with that one path using adaptive time stepping. So that's the idea of introducing this terminology here. So we consider the cost to be written as such. So basically, we count the number of time steps that we use inside of until the process basically exits for just one realization. And then we take the expected value of this and compute the expected cost that's associated with it. So in order to have a low computational cost, the number of time steps that you take should be low. That's basically what we would like to have ideally. So if a process gets stuck inside the critical region for a long period of time, you end up using very fine time step sizes, and the process stays inside the critical region for longer. So you end up generating more cost when you are implementing the algorithm. Let's put it that way. So in order to measure the amount of time that is spent by the process inside the critical region, we represent this term here, which basically relates to the occupation time. So the time that the process spends inside of the critical region, and we can show that it's of order delta squared for the order 1 scheme, which ultimately relates to it being of order h log h. There's a big proof which follows this. If you are interested, there's an archive paper which you can refer to. Reference to that will be provided in the end. So if you want more details into this, please feel free to have a look into that. So here we make an assumption that the cost associated with just one evaluation of the numerical scheme, which was given by psi of gamma, is of order 1. And we also define this running minimum sign distance. So if the process is inside the domain, the distance from the process to the boundary is positive, and if it's outside, then it's negative, and like vice versa, basically. And this is the theorem that we have also proven in the paper, basically. So under the assumption that the joint density between the process and its running signed distance is bounded, at least inside the critical region, you can show that under the assumption C, which was given before, relating to the cost of sampling one numerical scheme being order 1, that the total expected cost is of order h to the power minus 1 times log h. So what this basically means is you can end up using higher and higher order algorithms with more critical regions, and choose the critical regions in such a way that the total computational cost is still going to remain the same order as given here, but you end up getting a better strong order convergence. So which is a win in the sense that you improve the strong rate without increasing the cost that's associated with it. So here's the idea behind the proof. So you basically take the expected value of the cost of one realization. So you have like the expected value of the cost for like multiple realizations overall. You basically split the term based on the time step size that you use. So if you were to use the Milstein scheme, you would either use time step size h when you are outside the critical region, or time step size h square when you are inside the critical region. So you basically use the indicator function in order to differentiate between the two happening. And you can basically bound it from above by the fact that the first term here is going to be bounded from above by t over h. And the second term here relates to the occupation time, which was shown before in this slide, the equation number 5. And we know that to be of order h log h. And since we have a h square in the bottom here, the overall rate is going to be of order h to the power minus 1 log h. So this is the idea behind the computational cost. So in order to show this, there's no better way to show this rather than using some numerical tests. So the first test we perform is using a linear drift term and a nonlinear diffusion term. And the diffusion term is bounded in this case inside the domain. We consider that it starts inside a disk, basically with at center 3, 3. And the disk has a radius 3 as well. And we are interested in computing the time that the process defined above takes in order to exit that disk, or until it reaches the terminal time 10. So that is the numerical test that we perform. And in order to compute the strong rate, we make the assumption that the strong rate is similar to the order here, where nu L and nu L minus 1 relates to the numerical exit time for levels L and L minus 1. So this basically just follows from the multi-level Monte Carlo way of thinking, where at level L, we use the time step size h equal to 2 to the power minus L. And at L minus 1, similarly, you would have time step size 2 to the power minus L minus 1. It is important to note that in order to compute the strong rate, using this multi-level Monte Carlo idea is to basically ensure that between the levels, they share the same driving noise. So that's a key point one has to note. And this combined with adaptive time stepping, you can show that the strong error is of the order as shown before. So in order to test if our method actually worked when computing the exact expected value of the exit time, we compute the reference solution to it using the Feynman-Katz PDE, which we solved using finite element methods. And then this is just a plot representing the result, basically. So if you start very close to the boundary, you see that the exit time is like really low. But if you start somewhere here, based on the dynamics of the stochastic process, you end up staying inside the domain for a lot longer. And that's basically what can be interpreted from this image here. So as you can see, for the order 1 scheme, if I were to use the Milstein scheme here, you see that you get the order of convergence 1. And if I were to use the order 1.5 scheme, I basically improve the strong error rate of the exit time computation. And this also in turn improves the weak error, as you can see here. So in this case, the weak error is computed as the terminology given here. So we will also see that this basically corresponds with the weak error that you compute from the exact reference solution as well. So you get a slope which is very like similar to what you would expect from the previous plot. And this is relating to the computational complexity involved with implementing the higher order adaptive method. And you see that both order 1 and order 1.5 methods give the same order of complexity with respect to the time step size that you choose. So this basically provides a case where we can use higher order strong Ito-Taylor schemes with more critical regions and still end up with getting good convergence rates and also good complexity results. So in order to summarize what has been shown so far, we developed a higher order adaptive time stepping algorithm in order to compute the exit time of Ito diffusions. We were able to show that using adaptive time stepping with suitable choice of critical regions, you can improve the strong rate as well as the weak rate associated with exit time computations. We were able to show that the strong rate was of order h to the power gamma minus some epsilon, where epsilon is greater than 0, corresponding to what order scheme you use. In our case, we showed it for both the Milstein scheme and the order 1.5 scheme. And we were able to show that for both numerical schemes, that the computational cost involved was of order h inverse times log h. So what can be done in the future? So the first idea that like would strike our heads is to use multi-level Monte Carlo method with this adaptive time stepping and see if you can actually improve the performance of the of computing the mean exit times. And second extension would be to look into payoff functions that don't just that doesn't have to do with just exit time itself, but states or like functions relating to the exit time and the exit state. Third extension would be to consider looking into using other higher order schemes in order to improve the convergence rate. And fourth would be to try combining this algorithm here with this boundary shifting method, which was shown before, and see how it performs or if it actually does improve the convergence rate and the computational complexity involved. And Another idea would be to consider time-dependent domains, so domains that change with time, and consider domains that have a lower regularity, and see if this basically translates to such settings where the regularity of the domain is coming into question. So that's basically the extensions that can be done to this current study. So these are some of the references. Like I said, there's an archive preprint relating to our current work. If you're interested, please do go have a look into it. And if you have any questions, I'm happy to take them. Thank you for your time.